Okay. All right, good, we're starting. So the exam is going to be two parts. Part one of the exam is going to be 4 FE questions. So that during that portion of the exam, the only notes that you will be allowed are the packet FE handout. So make sure you take at least a little bit of time while you're studying and look over that. I think it's a good resource for you to build kind of your own. These are the highlights of things that I should have in my note help sheet. The exam itself is going to be, so there's going to be part one where you just get this packet. Part two, you're going to get whatever you want. So part two is going to be just open notes. As you're working, putting things together, we've done, I would still recommend trying to do some compiling and stuff, but you've already done that for previous exams. But because it covers all of the stuff that we've done, I'm assuming you don't have everything at the tips of your fingers, but if you can sort through and figure out stuff, that's really what we're looking for anyway. So part two is going to be open notes. Part one is going to be where it's a little bit weird because you have just a set packet of notes for that. Any other questions regarding what that's going to look like? Yeah, Barry?
So, sorry, is that what people can, you can use textbook and stuff?
So I'm somewhat on the fence. So the question was about a textbook. I'm somewhat on the fence about that because I know some people have virtual textbooks. So I think that that's not going to be the same for everybody. So I'm thinking no textbooks, but yes, notes. Just so that we're all kind of on the same page. Because I know some people have real books and some people have not real books. And you can't really use the virtual book because they're cheap, but trash. We deal with them because they're cheap. Yeah, so I think, open notes, but no book. The other thing, just to remind, really the problem part of the exam will cover up through the stuff that their discussion of similarity. So it's not going to cover, we're talking a little bit more about drag yesterday. We'll talk a little bit more about that today. That's not going to be on the exam in problem form, but there will be one question on the exam that's kind of more conceptual. It will have a couple parts on different topics, and something from the last couple days could show up on that, but it will be in a sentence explain X. So it's not going to be do a calculation, but it might be a 10-point thing or something like that, a 5-point thing. So it's not going to be a huge part, but it could show up somehow. Yeah.
Our last homework, that's not going to be on there.
The last homework, yes.
Okay.
So the last homework, the similarity stuff, yes.
Yes, so will be on.
Will be on the exam. Yes. Yeah, good question. Thank you. Okay, so we're going to dive in and talk a little bit more about drag today. Something we haven't had a chance to spend too much time on, which is a little unfortunate because there's a lot of cool stuff that we could do. But we'll spend a little bit of time today, and then we'll finish with, okay, another question from the chat. Will there be any Navier-Stokes derivation stuff on the exam? The answer is no. If the Navier-Stokes kind of shows up, it could show up some aspect of it, again, in a short answer problem. So having a general familiarity with what are the different parts and what it's doing. The other way that it could show up would be kind of how it showed up on the last exam, where it's here's a result from the Navier-Stokes equation, now do something with it. But it'll be you're given the equation, you're given the result. You're not going to have to come up with the result yourself. So there won't be derivation type stuff. Yeah, no way.
Will there be any of the external flow or pressure?
So the external flow and pressure drag could show up in a conceptual question, not a calculation question. And again, I'll try to keep like Moodle so that you don't have to remember all of this stuff, but it should be there. And if you have questions, shoot me an email so that I can help answer that. Okay, so are we, okay, I'm sharing there, but not everywhere. All right, so I should be sharing my screen. So when we're thinking about drag, this is what we'll start out with today. We watched a couple videos about drag, some of them with kind of weird results, like the soccer ball video where they have all these different designs of soccer balls. Why are they behaving that way? Why do you design it that way? And the video where we watched like a couple different experiments and we had to try to describe what was happening. So we'll try to describe a little bit what's happening in those experiments. So if we think about drag, we have two components. We have viscous drag or skin friction. So this is from, right, like tau yx equals mu du dy, from shear stress in the fluid from viscosity. So this is from shear in the fluid. And ultimately, this looks like it does in pipe flow. Okay, so again, just like conceptually, you can think about it in some of the same terms. So the same types of factors. Higher Reynolds number is going to give you more friction. Like higher velocities are going to be more friction. If we have a rougher surface, higher surface roughness, that's going to be higher friction. The same types of things conceptually. So that's viscous drag, but that's only the one half of the equation. And at high Reynolds number, this is typically the least important part. So I'll write that. So typically, small at high Reynolds number. So in a lot of systems, it's there, but it's usually not the dominant factor at high Reynolds number. So oftentimes the dominant factor at high Reynolds number is pressure drag. So this is often dominates at high Reynolds number. And it's really, if you want to think about it, it's the result of a low pressure weight behind our object. I don't know why my screen is making my handwriting. I promise my handwriting is not that bad. It's not great, but the computer's freaking out. Okay, so again, we talked a little bit about what this looks like and why. We're going to just go over briefly. Remember, we have, well, we'll look at the picture for laminar flow again, and over here we'll look at turbulent flow. So in laminar flow, you know, if we look at the surface of an object, say a ball, at the point where, right, if you think like instead of the surface, instead of the area converging, it starts to diverge. So at this pole, this is our lowest pressure. So what happens if you have the fluid at this point here, this boundary layer, what's happening is you have low pressure behind it because we're all of a sudden flowing into higher pressure because the channel is diverging, our fluid is slowing down, so pressure is going up. So we have low pressure on the back side of this, and we have high pressure on the front side. Okay, so what that's doing is that's causing all of the fluid to slow down. And if the fluid's moving fast, that's fine. It just slows down a little bit, right? Like you applied a force and it slowed down. But the fluid right at that surface is moving very slowly. So it slows down and can actually turn around and flow the other way if there's not something continuing to move it forward. So in laminar flow, what's continuing to move that fluid at the surface forward, there's the diffusion of momentum by viscosity. So again, think about it like viscosity is trying to drag that fluid and keep it moving. Pressure is trying to push it backwards and stop it. So it's a balance of who's going to win. And in a sphere, pressure is going to win and cause that fluid to stop and turn around. So pressure difference slows the boundary layer fluid if viscosity can't pull it along, the flow separates. So what we have in that case, again, we drew this last time, but we have our ball and we have the flow separating, and we get this a low pressure wake behind our object, and we get boundary layer separation occurring basically at the poles of the object. Okay, so in laminar flow, viscosity is the only thing that's trying to kind of overcome this pressure difference. And in a sphere, it can't keep up at high Reynolds number. At super, super low Reynolds number, then it can, because then viscosity wins. But at very high Reynolds number, it's not going to be able to keep up. So we get this low pressure wake, and we get high pressure on one side, low pressure on the other. What happens in turbulent flow is we flip the physics a little bit of what's happening in that boundary layer. So in turbulent flow, we have the same kind of picture where we have, this is our lowest pressure. And if we were to look at what's happening in the boundary layer, right, we have sort of mixing where you can take fast fluid from far away from the object and actually like swirl it in and mix it up with the slow fluid that's close to the surface. So we get, I'll try to draw this as a thick squiggly line. So this, we still have low pressure behind and high pressure above. Zoom in a little bit. So we still have low pressure behind, we have high pressure above, but we get momentum transfer by turbulence. Essentially, we get mixing in the boundary layer where the fluid is not allowed to slow to a stop because it slows down a little bit and then fast fluid mixes with it and they swap places. So we get, again, we have the pressure difference. Slows the fluid. But slow fluid mixes with faster fluid because of turbulence. So the net effect is that the fluid doesn't slow down, slow to a stop, and turn around as easily. Because it's going to start slowing down, but then it's going to mix with something that's moving faster, and then that's going to slow down a little bit, but it kind of constantly keeps mixing. So you never get this point where you don't get to this point as easily, where you slow down to a complete stop and turn around and actually separate from the surface. So you get, in this case, right, a ball like that, you'll see the fluid stays and follows the curve of the ball a much longer. So it doesn't separate at the poles, it can actually follow the curve of that surface. And you still get, with turbulent flow, you can still get a wake. But we have a smaller wake than we did for a laminar boundary layer, because we changed the physics. So now we have our boundary layer separation is delayed further down the back of the object. So we have a smaller wake, we have less pressure drag. So we essentially swap, we would have, in the case on the right, we have more viscous drag because turbulent flow has more viscosity, more viscous drag. But that didn't matter too much. So we dropped the overall drag because we got a smaller wake, and that means we have a smaller pressure drag. So you can do that if we look at this video that we watched some time ago now. We'll watch little bits and pieces of that and try to use kind of this framework of the pressure drag and the wake of the object to understand a little bit what's going on. Okay, so all right, you guys see? Okay, do you remember this video? So this was experiment number 1. Remember this was just a single smooth ball.
Start the motor now. Here we go. You see that we have got the speed up to about 75 miles per hour, while the drag force reaches about 1.5 units on a scale. I'm now going to increase the wind speed to about 100 miles per hour. So you can see it's about 100 miles per hour, while the drag force has increased to something a little less than 2.5 units. Now I am going to increase the wind speed continuously, and I'd like you to observe what happens to the force on the scale. Here we go. Up, 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 up. But now it's going down, down, and up again. Up, up. She's continuing to rise. Continuing to rise. And now it's very quickly, and it's not quite clear what happened.
Okay, so let's.
Yeah, but it's already one with you. When the speed reached a certain value, we found that a further increase of speed caused the drag to decrease. Increase of drag.
Okay, so just to have this graph to look at. So what's happening here? Well, at low speeds, what we have is things behaving kind of as we would expect. So what we have is we have a laminar boundary layer. So we can't see it visually in this experiment, but you have the flow separating at the poles of the sphere, and you have a big wake behind the whole thing. But eventually what happens is you get a fast enough flow, a high enough Reynolds number, that the boundary layer switches from laminar to turbulent. And once that happens, then we get the flow is able to stay attached to that surface longer, able to follow the curve of that surface because we have mixing now in the boundary layer, so you can't slow it to a stop as easily. So then all of a sudden you drop the total amount of drag by almost half because you have decreased from a huge wake, like the size of the whole object, to a very small wake. So you've decreased pressure drag, despite the fact that you've increased viscous drag. So it's this kind of balance between these two components. The other experiment, experiment number 2 that we watched, remember this experiment? So this experiment, we had 2 balls. We had one that was smooth and one that was rough. At low speeds, the smooth ball won. The smooth ball had less drag. So why did that happen? Well, the smooth ball had less drag because the drag was primarily, so it had less viscous drag because it has a smooth surface, so the flow goes over it and there's not surface roughness. But that roughness can help flip the flow, like it can cause disturbances in the flow. So it makes it mix up in the boundary layer and can get you to where the fluid in the boundary layer doesn't come to a complete stop because you're causing this same type of mixing as what we see in turbulence. So this is the same idea behind a golf ball and a baseball. And that soccer ball video that we watched, right? The reason that it matters so much, exactly what the surface of your soccer ball looks like, or your golf ball, or your baseball. The reason all of those things have rough surfaces instead of smooth surfaces is because that surface roughness causes mixing at the surface, which delays boundary layer separation and you get a smaller wake. So the reason you have a lumpy golf ball is because it has a smaller wake than a smooth golf ball would. The reason, like soccer balls, you really have to be careful what the seams look like and how that works, in baseballs too, because those seams, those surface defects mix the boundary layer and make sure that it doesn't come to a stop and separate from the surface. So it's delaying boundary layer separation. It's giving you more viscous drag, but less pressure drag. We can use some of the same kinds of arguments for this last experiment. So this last experiment, instead of doing something with the, to make a turbulent boundary layer, instead of inducing boundary layer mixing, we changed the shape of the object. Right? So in this experiment, we went from a ball to a bomb shape. So what happens is, right, your pressure, right, pressure and velocity are linked. So as velocity goes down, pressure goes up. So if that happens fast, it's a really quick change in pressure. That's what happens at the backside of a ball. It's a fairly steep change in shape, so the pressure goes up quickly. When the pressure goes up quickly, viscosity isn't enough to keep the boundary layer attached. Like viscosity loses that battle to pressure change. But if we elongate the shape and make the pressure change only very gradual, right? So like a bomb shape. Then the pressure change it still changes, but it's gradual. So viscosity is enough to be able to overcome that. So in that bomb shape or a streamlined shape, the streamlines are able to follow the entire curve of the object. That's why we call it streamline. So there isn't a wake in that shape. So that's why you get these weird effects where a lot of times to make something more aerodynamic, you make it long and pointy on the back end. You've ever seen like a bicycle helmet that's designed for like road biking in the Olympics? You'll see these weird, goofy things that go like way backwards. The reason that those do what they do is, and the reason that like this bomb is shaped the way that it is because that gradual decrease in angle allows the flow to stay attached to the surface longer because you have a less dramatic pressure increase on the backside, which is kind of a weird counterintuitive thing, right? But this is why canoes are shaped the way that they are, right? A canoe is long and skinny on the back end. That's a faster shape than if it were blunt on the back end. Because if it were blunt on the back end, then it's going to form a wake because the water can't follow the curve of the boat the whole way like it can in a canoe. So in a canoe, you have less pressure drag behind you because you have a small wake than if you were to just like lop off the back end of the canoe. Same idea with fish. Right? Fish are all shaped kind of long and they gradually taper to the tail. The reason that they do that is because that gradual curve on the backside of the object is what allows the fluid to stay attached to the surface and gives you a small wake and less pressure drag. It's giving you a longer body, so it's giving you more viscous drag because your surface area is bigger. So that's what happens in this last experiment, where he takes these two, if you remember this one, he takes these two objects now and puts them in glycerin, which is really thick. In this case, the viscosity is big enough, is strong enough that viscosity wins in both shapes. Like viscosity is enough, there's enough viscous force to keep the boundary layer attached to the whole shape in both cases. So then viscous drag is the only thing that matters, and having a small surface area lets you win in this case. But in a lot of cases with high Reynolds number, we have this balance between basically what can you do to decrease the wake that's behind your object. So you'll see that especially in aerodynamics, but also in things in like liquids and stuff. You'll see that a lot, where actually often what matters the most is not what you do to the front side of the object, but what you do to the back side of the object, which is kind of this weird counterintuitive thing that you're not trying to, like the initial thought that you might have is you would try to like cut through the air, or cut through the water, which is part of it, but it actually matters more what you do on the back side, on the reverse side of your object, in a lot of cases. So anyway, some kind of fun things. The last thing that we're going to talk about is, we won't talk about, I'll let somebody else talk about, is non-Newtonian fluids. So a non-Newtonian fluid, a Newtonian fluid is stuff that we've been talking about all year. So we'll spend 10 minutes talking about all the other types of fluids that exist. A non-Newtonian fluid is something that just doesn't behave like a normal fluid. So there are a number of different types of non-Newtonian fluids. So if you look at, okay, I just lost it. Where did it go? There it goes. Okay, so Newtonian and non-Newtonian fluids. So if you look at the graph on the right, let me zoom in, and it's probably going to move me again. Wonderful. Okay, so if you look at this graph, this is just from Wikipedia, but I think it does a nice job. That graph on the right, what normally happens in normal fluids is shear stress and the shearing rate, the change in velocity, the slope of the velocity, those are linearly proportional, right? We have this equation tau equals mu du dy. The shear stress is equal to the viscosity times the shear rate. So that's how normal fluids behave. If you like try to shear them faster or use like, you know, higher velocities, they offer more resistance. But there are some fluids that do really weird things. So there are some that are shear thinning, where like the more you push on them, the more liquidy they get. So they start like really thick, and then you push on them really hard, and then they're really like liquidy. There are some that are shear thickening, where they start kind of, if you gradually push them, they're liquidy, but if you push on it really hard, they feel like solids, or they get thicker. And then there are some that start out kind of as solids, but once you push on it hard enough, then it transforms into a liquid. So we'll look at a video, and I'm gonna just give the caveat that this is designed for like first graders, which is why